I'm going to dive right into this. I have 15 minutes to teach all of us all about geothermal heat pumps. Hopefully, we'll be able to internalize our collective ability and necessity to implement this technology going forward and make these changes. And we're going to leave with the intent to not only want to try geothermal in our own homes and communities, but we're going to recommend it in every application going forward. So watch for this. That's a big commitment. See if you don't agree by the time we get done. Let's start by looking at a standard geothermal system. Every geothermal system of which I'm speaking has three components. It has a ground loop or a ground exchanger from which the heat pump gets its energy. It has a heat pump that actually does the work of heating or cooling based on that energy exchange, and it will have a distribution system. That's going to be either the duct work, like you have a forced air duct system in this room. It's going to be a radiant floor. It's going to be radiators along the wall or something of that nature. There are three ways to transfer heat, and this is important because one of these three ways is the way that a building is heated or cooled. Whenever you're inside of a building, you can look and identify one of these: radiation, convection, or conduction. Radiation is what you feel. Everybody has seen a radiator. If you stand in the vicinity of it, you get electromagnetic waves that turn into heat energy when they hit a solid object. You have convection, which is forced air, the bulk movement of molecules through a duct system. It's either heating or cooling. And then you have conduction. That is when you would be able to slip your shoes off and you have a conductive radiant floor and it feels warm to the touch. You can feel that and it feels comfortable. And that also doubles as a radiation source. In order to truly understand the magic of heating appliances and cooling appliances, you need to understand how they're rated. They're rated in something called coefficient of performance. For example, a gas furnace, if it's good, is going to be between 90% and 98% efficient. That's a 0.90 coefficient of performance. An electric resistance heat strip, for example, a room heater or a blow dryer, is 100% efficient. It has a COP of 1. So hopefully that makes sense. Let's move on from there. Let's talk about, before we talk about how efficient geothermal heat pumps are, let's talk about what a heat pump does, really and truly. If you want to get water from the ground, you drill a hole in the earth. It's called a well or a borehole. And you insert something with a motor in it called a water pump. That water pump pumps water up to your building where you can bathe in it, drink it, wash with it, whatever you need to do. If you put a water pump on this stage, on this podium, and put power to it, would it create water? No, it cannot spontaneously create water. A heat pump is exactly the same. You put a heat pump in a building, you bore a hole in the ground, and you put pipes in that hole, and it can extract heat from the ground, or it can, in reverse, pull heat from the building and put it back into the ground. A heat pump is not a heat-creating device, it's a heat-moving device. Once you understand that, you're ready for this next part. If you look at the house with the snow-covered ground, that house is trying to extract heat from a cold environment, except that it's going into the 55-degree ground, so it has an advantage, right? Because no matter how cold it is, minus 10 degrees out or whatever, it's 55 degrees in the earth. So it's going to be efficient. The same thing is going to happen in the middle of the summertime when it's 90 degrees outside. It's going to be pulling heat out of that house, which is acting as a solar collector, and putting it back into the ground. 55 degrees, much easier. Let's look at an example. I love this diagram because for 1 unit of electricity from the electric grid going to this heat pump, it's going to use that unit of electricity and pump 4 units of heat out of the ground. You add the two together and you get 5 units of heat in the space. For 1 unit of energy, you get 5 units of heat. That's a COP of 5. It is 500% efficient. That's how that magic happens. Let's talk about your refrigerator in your kitchen. Your refrigerator is a heat pump. It is a device that pumps heat out of the box, creates a 40-degree box in the main refrigerator and a 5-degree freezer up top. It's pumping heat out of the box. It's a heat pump exactly like what we're talking about here. When you have a heat pump in your house, a standard split system, you're pumping heat out of the house through a condenser outside. It's operating exactly like a refrigerator. Reversing that, it can pump heat from the outside back into the house, or if this refrigerator was operating as a hot box, it would be pumping heat into the space. This is the science of it, and it's called the Carnot refrigeration cycle. It always uses 4 components: a compressor, a thermostatic expansion valve, a condenser, which does the heating, and an evaporator, which does the cooling. So, depending on what mode you're in, you're either cooling your house or heating your house because it reverses and switches the way the refrigerant flows, doing the heat pump mode. There are 2 fundamental ways to move energy through a building. There are really more than this, but this is what I'm going to talk about here. A forced air duct system or a hydronic pipe or a pipe filled with water. In a forced air duct system, this 8x14 duct moves as much energy as a 3/4 inch pipe. Hydronics are a more efficient way, not only for that reason, but because of the fact that in that pipe you lose 7 BTUs per foot per hour. In that duct, you lose 10 times that amount. So when you're talking about larger systems, maybe a school or something, it's much more efficient to distribute your energy through the building through a hydronic pipe. It's actually more efficient than distributing energy through a building using refrigerant for several reasons. NYSERDA is in the midst of testing fluids that not only increase the efficiency of moving that energy through the building, protect against freezing, but also is safe for the environment. Low viscosity plus health and safety equals solutions. Now let's talk a little bit about, we're going to hear about air source heat pumps, which are a huge part of the solution in New York, electrification. But ground source heat pumps, as shown here in the American Society of Heating and Refrigeration and Air Conditioning Engineers, they're building in Atlanta. They decided to install the first floor with air source heat pumps and the second floor with geothermal heat pumps. What is shown here is what happens. When it gets really cold outside, the air source heat pumps can do the job, but it peaks out on energy efficiency during that time. Part of the solution is keeping the grid stable. And as you can see by the red lines and the blue lines, the geothermal heat pump has an unfair advantage. And what is that? The ground is the same temperature year-round, where the air temperature fluctuates seasonally and causes it and changes the efficiency. 2 buildings in Oklahoma City in the right graph show the same thing. During the middle of the winter, it peaks out terribly in those cold weather temperatures. Let's look at a National Grid slide for just a moment. National Grid has a peaking electrical issue because of all the cooling that goes on in Long Island. In the wintertime, it has a peaking natural gas issue. Now, if we had 100% penetration by geothermal heat pumps, we would shave the peak off of that summertime, and then we would add load to the winter time because the heat pumps do use electricity during the winter. But they level it and they optimize the use of electricity year-round. That decreases the cost per kilowatt and increases the efficiency of an electrified society. New York, reforming the energy vision, says we've got to reduce emissions by 40% by 2030. The only way to do that is to turn off the gas. You're right in the middle of it here. We're turning off the gas, and we're going to a renewable, sustainable, clean heating and cooling source. If you want proof, look at the bar graph, those cylinders on the right. Those are all fossil fuel heating appliances on the left. The one second to the right is an all-electric home using an air source or an all-electric source of heating. The geothermal heat pump is using even 1/3 of the electrical heating and energy consumption. And I saw it just this morning. I had to answer a question on a social media post. What if the energy plant is using coal or natural gas? That is not our problem as consumers or legislators. It really isn't. The grid is green from the International Energy Agency as of 2020, 30% green worldwide. And by the time we hit 2050, it's going to be 70%. Our only job is to go all electric. When we do that, we're on the right path. Here's what it looks like. Here's the mess you're going to see in your yard when you drill. It might be one borehole, it might be three, like in the case of this. But the beauty of it is it's one time. The infrastructure's in, and then that's what your yard looks like, or your school, or your football field, or your whatever you're putting in. And it even gets better than that on larger systems. So don't worry about the infrastructure. It's going to be there forever. Here's what a geothermal heat pump looks like. They're generally the size of a forced air furnace. And they go into a closet, above an attic, wherever you want in your building. No more outdoor equipment to worry about. Hurricane proof. Why? It's inside. Longevity, because there's nothing outside to wear away. No combustion, superior heating and cooling, remarkable system efficiency, the best system efficiency you can possibly get, and you're dealing with permanent infrastructure. If I were to start talking about the variations in geothermal exchange, you'd be here for 8 hours. So just look at the picture and know that there are a lot of ways to do it. Do you know what? People a lot smarter than me will help you do that. I just love to talk about it. What's this energy source, though? What are we doing? Take a look at these pictures. 49% of the energy that strikes the atmosphere is absorbed by land and surface waters. The Earth is a great big solar energy battery. We are using a solar energy heat pump. Isn't it beautiful? It's solar energy, essentially. And when you're doing geothermal, you can share energy between multiple buildings and purposes. In this zoo, the polar bear exhibit, the heat extracted out to keep it cool goes in to heat the elephant exhibit. The same thing happens in communities like YMCAs and so forth. Do you think there's a geothermal heat pump to fit your application? I guarantee you there is. Look at all these heat pumps here. This is just the beginning of it. Whether you're talking rooftop package unit, 100% fresh air units, no matter how big the building, there is a solution for you. Infrastructure in your community can help provide a geothermal exchange utility. You got to think big. Are you tearing up the streets? Put in a geothermal ambient line. It's the way to do it. It eliminates the wells. And there are so many different exchange mediums out there. Fresh water, effluent water, wastewater, runoff. The list goes on. All the possibilities are there, and that's another 8-hour conversation. You decide to do it as a government, as a legislator, as a consumer. We will help you do it. Geothermal systems increase building performance and comfort, public health and safety, huge public health and safety issue, greater energy efficiency, eliminates cooling towers and boilers, enables water savings, increases longevity, and eliminates combustion heating. Thank you.